Hello, this is section 7.2 from the James Stewart Calculus text, Early Transcendentals, and we are talking about trigonometric integrals today. So in a nutshell, before you see the rule set for calculating an integral that involves powers of sine and cosine, and we'll move on to powers of tangent and secant, and also other techniques of integration involving trigonometric functions. So here before you, the basic idea, if we've got an integral of f of x dx that involves a power of cosine and a power of sine, we want to look at the powers that we have there. Now, of course, if we can do a standard substitution, in other words, if one of those functions has power equal to 1, then we can do a standard U substitution of letting U equal the, let's say for instance, sine x there was just sine x dx and not a power, and we had like cosine cubed of x times sine x dx. We can go ahead and let U equal cosine x and use a standard U substitution. But what if both powers are higher than that? So here's our basic rule set. If the power of sine is odd, then we want to split off one of the sines, and that will actually be part of the du. Okay, because we are going to make a U substitution, and you will see down below, if that's part of the du and we're going to borrow a sine U, notice that we're going to let U equal cosine of theta. And what is the derivative of cosine of theta? Minus sine theta d theta. So that's why I say it's part of the du. And that will apply to other trig functions, powers of trig functions with secant and tangent. Next up, we will want to rewrite the remaining powers of whatever we split off. So if we had powers of sine or odd, then if we split off one of them, then we all of a sudden have an even power of sine. And if we have an even power of sine, then we can use our fundamental trig identity to rewrite our expression, knowing that if we have an even power of sine, we can always rewrite this trig identity as sine squared theta equal to 1 minus cosine squared theta. And that's what we would want to do, is replace whatever powers of sine, which are even, with 1 minus cosine squared, so that we get an entire expression in cosine. So then if we get an entire expression in cosine, then we can do a U substitution of cosine and transform our integral into an algebraic expression and easily integrate. The same rule set goes for if cosine power is odd, then we would want to split off a cosine, and again that's also going to be part of the du. And what function has derivative equal to cosine? Sine does. And notice that our rule set here is that we're ultimately going to let U equal sine theta, so that du is what we split off from our power expression. So of course we're still going to use the same fundamental trig identity, and note that if we're splitting off one cosine, we're left with even powers of cosine. With even powers of cosine, we can make a substitution of our fundamental trig identity, knowing that cosine theta is 1 minus sine squared theta. And once we substitute all values of cosine to be in terms of sine, then we can let U equal sine theta and transform our expression into an algebraic form and integrate easily. Now, problem arises if both powers of sine and cosine are even. Well, then we can introduce our half-angle trig identities, and whenever you see sine squared and we don't have a cosine theta d theta that we can make a standard U substitution with, or if sine squared theta is by itself, or if we have sine squared times cosine squared and neither one of them are odd, then we will want to use these trig identities. We'll want to substitute sine squared for 1 minus cosine 2 theta, and we will want to substitute cosine squared with 1 plus cosine 2 theta over 2. And keeping in mind here that 1 plus cosine, just as an example, 1 plus 2 cosine 2 theta over 2 does equal 1/2 plus 1/2 cosine 2 theta. And if we had to integrate this expression here, it would be easy to integrate 1/2, and it would be easy to integrate cosine of 2 theta d theta using a U substitution, a standard U substitution of U equal to 2 theta. So, but of course, in some instances, it might be more complicated. You might need to manipulate the expression even more, but hopefully you get the idea of how to approach a cosine squared. All right. Now, in our basic table, we do have the integral of cosine theta d theta. We have the integral of sine theta d theta. We can do the integral for tangent using a U substitution and get ln of secant x. We can also do the same for cotangent of x, but finding the integrals of secant x dx and the integrals of cosecant x dx are a bit more involved and involve a unique trick of multiplying on the top and bottom by a special version of a trig expression. So these still end up in the basic trig or basic integral table. So just keep in mind that every single trig function is in the basic table of integrals and can be easily located. All right. Well, the rule set for finding integrals involving powers of secant and powers of tangent are a bit more involved because remember that integration is the inverse process of differentiation. And if we recall that the derivatives of tangent are secant squared and the derivative of secant is secant tangent, then it's a bit more tricky in setting these trig integrals up. But keep in mind, whatever you split off from your powers becomes part of the du. So again, if your powers of secant are even, we're gonna split off whatever we split off. This becomes part of the du, which kind of gives you your motivation. What function has derivative equal to secant squared? Tangent does. And notice in this process that we're going to let u equal tangent theta. Now, we're still going to use our fundamental trig identity, 1 plus tangent squared. And if we're splitting off part of the secant, we want to express the remaining parts of secant. And since they're still even, we want to express that remaining part in terms of tangent. So recall here, if we just make that manipulation, we are seeing that secant squared theta does equal tangent squared theta plus 1. And once we make that substitution, then we can do a U substitution, and it will be easy to calculate the integral. Again, for powers of tangent, if tangent is odd, then we're actually going to split off a secant tangent. And again, that is part of the du. And what function has derivative equal to secant tangent? U equal to secant tangent. So that's what we're moving towards, is making a U substitution of secant. So again, we'll want to take the remaining powers of tangent and express them in terms of secant. So if we take a look at our fundamental trig identity here and just solve for tangent squared, and we'll have remaining even powers of tangent, so we can play with this. And that will be secant squared theta minus 1, right? And we'll want to make that substitution everywhere, and then make a U substitution and integrate easily. And of course, to finish off this, we will want to back substitute so that we end up with an answer in theta. Now, if both n is even and m is odd, you can either use the first two methods, right? Both will look different, but they will yield identical answer, or they will yield trigonometrically identical answers. In other words, they might not look the same. So in other words, if secant is even and tangent is odd, you can choose either method, but your answer will not look the same. But if you use fundamental trig identities, you will note that the family of functions there is identical. So they are trigonometrically identical. And of course, with cosecant and cotangent, because they have very similar derivatives, you can use the same technique there. Okay. Finally, if we end up with different arguments, so in other words, if we have different inputs for sine and cosine, so m and n are assumed to be different values, then we can't use a straight substitution for that. We would have to use a different technique of integration. So if we return to some of our trigonometric identities from a standard trig course, we have products of sine and cosine that can be transformed to sums. And that's what we would want to do if we have something like sine of 2x times cosine of 5x. So the idea here is to identify, are we multiplying sine times cosine with different inputs, sine times sine with different inputs, or cosine times cosine with different inputs. And it's a matter of just transforming that product to a sum and then using a standard substitution. So I thought I'd go over some examples of how to apply these rules. Okay, so in this instance, again, just as I mentioned above with secant and tangent, notice that the rule sets for sine and cosine are, if we've got an odd power, borrow one of that odd power. So what if we have both odd powers? It doesn't matter which one you choose, it's just a matter, and both outcomes will be trigonometrically identical. But in this case, I think it's easier to play with the smaller exponent, because then it makes your trigonometric substitution in that second step easier to make. So in this case, I'm going to play with the cosine as odd and cosine is the third power, and I'm choosing the smaller one because it will be easier to substitute. And I'm just going to move the 3 on the outside. So I see the constant 3, and that's going to be cosine squared x times sine to the 5th x, and I'm borrowing my cosine x dx. And I just put that there. This is part of my du. And that will tell me I want to transform the remaining part to be in terms of sine. So I'm going to say that this is equivalent to 1 minus sine squared x times sine to the 5th x times cosine x dx. And all I have done is changed my cosine. Now, since my cosine x dx is part of the du, I can say let u equal sine x, then my du is going to be cosine x dx, and now I can make my transformation, or make my substitutions. And this is going to be 3 times 1 minus u squared times u to the 5th times du, right? And notice that that transforms into an easily integrable algebraic expression. We want to make sure that we want to clear our parentheses before we integrate. And we will end up with 3 times u to the 6th over 6 minus u to the 8th over 8 plus c. And since we started with an integral in x, we want to end with an expression in x, or a function in x, and we can say that this is 3 times sine to the 6th power of x over 6 minus sine to the 8th power of x over 8 plus c. And that is our answer. All right, let's do another example here. And we have tangent squared secant to the 4th. Tangent is not odd, but secant is even, so we want to borrow 2 secant squares, and so this is going to be tangent squared theta times secant squared theta, and I'm borrowing the secant squared theta d theta, and that's going to be part of my du. We want to say what function has derivative equal to secant squared. Tangent does, and so we'll want to transform our entire expression to be in terms of tangent, so we'll want to transform secant squared. And we know that secant squared is equal to tangent squared plus 1, and so we have here tangent squared theta times tangent squared x plus, or theta plus 1, times secant squared d theta. Now we can make our U substitution. Our U is going to equal tangent theta, and our du is going to equal secant squared theta d theta, and now we can make a U substitution, and I see that that is going to equal U squared times U squared plus 1 times du. We can clear our parentheses, and we get u to the 4th plus u squared times du, and now I can integrate directly. And I end up with back substitution of tangent to the 5th theta over 5 plus tangent 3rd over 3 plus c. All right, one more example. Here we have tangent cubed secant x dx. I see that tangent is odd, so I'm going to split off a secant tangent. So if I split off a secant tangent, I end up with tangent cubed, or tangent squared of x times secant x tangent x dx, and that's part of my du. So that tells me what function has derivative equal to secant tangent. Secant does, so I'm going to want to transform tangent squared to be in terms of secant. So this becomes, using my fundamental trig identity, tangent squared is secant squared x minus 1, and we still have secant x tangent x dx here. We'll want to make our U substitution, and so we'll let U equal secant x, and our du will be secant x tangent x dx, and then we have an integral that transforms to u squared minus 1 du. We can easily integrate that to u cubed over 3 minus u plus c, and we want to back substitute, and we'll get secant cubed x over 3 minus secant x plus c. And we are done. Now let's see about cosine squared, right? So let's do an definite integral here. Cosine squared is not even, squared is not even, and so we want to use our half angle identity, and so in this case this would be 0 to pi over 2 of 1 plus cosine 2 theta over 2 d theta, and as I mentioned earlier, this would be the same as 1/2 plus 1/2 of cosine 2 theta d theta, just undoing that fraction addition or just factoring out the 1/2. I can split up using our algebra of integrals, to say that this is 1/2 d theta plus 1/2 times the integral of pi over 2 of cosine 2 theta d theta. The first integral is very easy to integrate, and that is just going to be 1/2 theta from 0 to pi over 2, and we're going to get 1/2 times pi over 2, take away 1/2 times 0, and we're just going to get pi over 4. With the second integral, we'll want to make a standard U substitution, U equal to 2 theta. Then du, it would be 2 d theta. And if I multiplied by 2, I'd need to divide by 2. So we would end up with a 1/4 here times the integral. And I'm going to have cosine of u du. If you want to change your limits of integration, when theta is equal to 0, u is equal to 2 times 0, which is 0. And when theta is equal to pi over 2, u is equal to 2 times pi over 2, which is pi. Good. And then we can integrate with respect to u and not have to back substitute. So here we go. What is the integral of cosine? What function has derivative equal to cosine? Sine does. And we'll have the plus 1/4 times sine of u. And now I can go from 0 to pi because those are my new limits of integration. And so this is going to end up being pi over 4 plus 1/4 of sine pi minus sine 0, and both of those are going to be equal to 0, and 1/4 times 0 is 0, so we will end up with pi over 4. Good. All right, I don't think I have any other examples here, but I just wanted to point out some trig integrals. If none of the rules apply, so in other words, if you're given both even powers of cosine, you'll want to transform using the half angle identity. If you are given powers of tangent and secant, if tangent is not odd and secant is not even, then you should go back to fundamental trig identities and try to transform your function into an equivalent expression where you can get somewhere. It's going to require more innovation and manipulation using identities to get somewhere. I might do another video on trig integrals just to emphasize that or demonstrate that. Thank you.